Let us try now another example of Ampere's law. Namely, the solenoid, sometimes called a coil, and it also makes up an electric circuit element that we'll be studying soon, something known as an inductor, which is the magnetic analog actually of a capacitor. It's a way to store magnetic energy. Now, we've seen this particular system before. If you recall, it looks like this coil. So again, to remind you how we draw one of these, our wire comes in, and then he begins to loop around, and I'll try to make nice generous sized arcs like so. We always come around and put a break when we pass behind ourselves so we don't lose track of what is in front of what, and it would look something along these lines like so. So current I would in this case flow in this particular direction. Now, and you can see then the current is coming up in front and down and back. Then it comes back around through the page, then back up in front and down and back. And the flow of the current then around this coil would follow the pattern that I'm indicating to you here. The geometric factor that controls how strong of a magnetic field we can get from this thing, of course, is going to depend upon how many loops we have in our particular wire, how tightly it is wound. So there's a particular parameter that describes that. It's very analogous to the parameter that we saw in the sheet case. And in that case, what we do is we look at the number of turns per unit length, and we call that lowercase n again. Lowercase n equals number of turns per unit length, like so. Very good. So let's now apply our procedure, our three-step procedure for determining the magnetic field in this particular case. The first step, of course, is to carry out that fluid analogy. We've looked at this before. I'll just take another quick look at it. It went a little quickly in some of our previous discussions. And that will give us some insight actually into some key facts we need to bear in mind as we actually solve for the magnetic field in this case. So you will recall the way we had done this previously was we decided to take a look at a straight halfway cross section that slices directly halfway down through this system to help us visualize it. So if I were to just simply slice through a plane that cuts this coil right in half, like so, and I were to sketch what I would see in that plane, what I would see would be a series of wires running around the top. I'll draw them as rather large circles so I can carry out the fluid analogy. Those represent the crossing points where each of these loops cross that midway plane up top, and then there's another series of crossing points when they come out down below. Here I want to give a little bit more generous space, and again write them here a little bit more large. And what we had seen previously again was that the current, recall, is coming up around in front. It goes down into the page here as it passes back. So these are all downward current flows, like so. And these are all then upward current flows on the bottom, like this, because once they come around the back, they had to come back out up in the upward direction as they cross through the bottom part of our plane. Following our right-hand rule, we can determine that with thumbs up, right, the rotation of my little rollers or wires goes something like so on the bottom. And then on the top, it's just the opposite way, thumb down. So things up top circulate clockwise. So they're circulating this way. The main point of all of this, or the first key point actually, is that what we have is coherent dragging of the fluid in the backward direction through the inside of this coil. So the magnetic field lines inside something like this are going to actually be fairly straight and all moving in the same direction, nice and coherently down through the center of the coil. Now, the key point to bear in mind is that if this is a finite coil, but one which is rather long, right, that these field lines, when they come out, they have a large amount of space in which to loop back around. The one I've drawn here doesn't look actually quite so large, but they've got a lot of space where they can loop here all the way back around. So the spacing in the field lines is actually fairly sparse when we get quite far away. The key conclusion from that is that, well, when I get infinitely far away from this thing, when I'm very, very far out here, the magnetic field way, way out here at large distances, b, we can take to be 0. And that's going to be important, because now what I want to do is imagine that I've got this field line pattern. I have to choose my Amperian loop. Now for my loop, what I want to do is I'm going to take some arbitrary position inside of my coil, right? And I want to run, say I want to know what is the magnetic field here at this position. If I'm at that position, in here, of course, my Amperian loop then is going to run nice and parallel, like so, to the field line. It then is going to cut perpendicularly, because I have to find some way to end this thing and make a complete loop. So it's going to cut perpendicularly to the field lines. That part is good, right? Notice I'm already beginning to include some of the current, so that also fits my criterion. But now this is where I begin to run into trouble. I can come outside here some distance, and out here I expect the field likely to be very weak, but I don't know exactly what it is. And if I were to terminate my loop at any finite distance here, I always run the risk that when I do that, there'll be some unknown magnetic field along this line, and I won't know what value to include for that field. So it's very important, actually, that I bring this loop super far out towards infinity. So I'm going to indicate that by putting a little break here in the loop. That little break there just signifies that I'm going out to an infinite distance, so that out here I, strictly speaking, do have the right result, that the magnetic field is 0 out at infinity. I'll put quotes infinity here, very far away from that solenoid. Okay, from this now I've got a complete loop, and I can now carry out Ampere's law. So let's write down Ampere's law in this case. So once again, what we have is that mu naught times the enclosed current equals the directed line integral around my path of B dot dl. Now, if I'm going to make I've got to use right-hand rule number 2. This is a directed line integral. I have to pick a direction for my path. So in this case, to make life easy, I'm just going to, and this is usually the most convenient thing, I take my point of interest here somewhere inside the solenoid, and I'm just going to begin my loop by moving along the same direction with the magnetic field. And then, of course, the rest of the circulation around this loop will then be down out this way, across back here at infinity, right, and then back up into the field. That then allows me to determine the positive and negative sense for my loop by the right-hand rule, right? Curling my fingers in this counterclockwise direction, the way that the loop is oriented, your thumb points directly up out of the page. So the normal direction for the surface is going to be outward. That means then that when I calculate the enclosed charge across, or the enclosed current across this entire surface here, what I'm actually trying to account for is positive currents in the same direction as n and negative currents in the opposite direction from n. In this case, all of the currents that I see are upward, so I'm going to get a positive contribution. So now let's try to evaluate that. So I'll have mu naught. The number of wires that I've included in here clearly depends upon the length I've chosen for my rectangular loop. So I will once again call this length here L. So the total number of wires that I've captured is their density, n turns per unit length, times the length that I'm accounting here so far, times the current. It's plus or minus, but as we've just been at some pains to discuss, it's actually the plus sign. And now for my loop integral, it's going to be the same story as before. In previous examples that we've done, we break our path integral into a series of components, just like we do for composite Gaussian surfaces. In this case, I'm going to have the top, the bottom, the left, and the right. So let's go through these. So there's going to be the bottom segment. I'll write that one first because I think we know what we're going to get for that line integral. Along this bottom segment, I've gone out to infinite distance, and so the magnetic field is actually 0 way out there, so I know I will get 0 for that case. I also know that the magnetic field lines, notice, are all running in when I'm inside where I have a significant magnetic field. They all run perpendicular to the left and right side. And once I'm outside the solenoid, I haven't drawn things for you, but if this is a very long solenoid, right, you can be assured that if I were to continue drawing these field lines, right, they are all going to be cutting very nice and perpendicular to these two sides. So the left and right side, I'll have a nice 90-degree angle, so I think we know what we'll get for those integrals. So there's the left b dot dl, plus there's the integral of the right b dot dl. And when I do that, then I have these dot products. They all give me a cosine, but the field, as we've been saying, is always perpendicular to this particular path. That's how we've chosen it to be. And I am cutting along these perpendicular paths, so that's cosine of 90 gives me 0 for this term. And again, this term will give me cosine of 90, so these terms will also vanish. And we're just left with the inside part of the integral, the top part of the loop, which has integral of b dot dl, just along this upper path here inside. Very good. All right, so now I think we can see how this is going to finish out. We're going to have the dot product we break out. It's the product of the magnitudes times the cosine of the angle. Now along the top loop, we've chosen, in fact, our direction of integration so that all of our little directed chunks as we break up our line integral, I'm not going to draw all of them, but they are all clearly in the direction of the magnetic field by construction. So we're talking about the cosine of 0, which gives us a 1. The magnitude of b, as long as I'm staying at constant distance here from the edge, I can be assured that that magnitude is going to be a constant value. And that constant value then I can pull out of the integral. And when I do that, as you can see, all that's left is the integral of dl. That will be the total length of the upper portion of this path, which is length L, because I've constructed things here as this particular rectangle. So that will just give me a factor of b times L. So to summarize, I've got then from the left-hand side, mu naught plus nLi. And on the right-hand side, I have the magnitude of b for this particular distance I've chosen inside the solenoid, a particular distance from the wall of the solenoid, times L. The L's cancel. And we have the nice, interesting result that the magnetic field intensity inside a solenoid is actually constant. It's mu naught n times I. Again, this is constant, independent of the depth inside the solenoid. That's a very nice result that we have there. Doesn't matter how far deep I go into that solenoid, notice I'm always going to get that same result. Now, that's nice and convenient. Now, what about outside the solenoid? Right? So far, all that I've managed really to argue is that the magnetic field at infinity should be 0. And I've also argued that, well, if I continued some of these field lines, right, and they were to cut back across like so, try to draw a typical representative field line, that I'm going to be cutting here at very nearly right angles. The longer the solenoid is compared to the size of my loop, the more and more true that statement is going to be. but I don't know yet really how strong the field might be here if I idealize this as an infinitely long solenoid. So we have another computation actually to do. I'd like to determine the magnetic field at some point out here, at some distance from the center of the solenoid. So let's take that as a sub-part of this example. Let's try to calculate the magnetic field at this position by following Ampere's law. If I were to do that, right, again, what I would do would be I would say, okay, I need to take a path always parallel or perpendicular to the magnetic field lines. So let me actually take this as my path now for evaluating Ampere's law, and I'm going to follow this path around my loop in this here particular direction. So this answer here was for inside. Let's try, I'll call this example B, part B. Outside. In that case, you'll notice I've broken one of my little rules here. This is kind of the one exception. I haven't actually enclosed any charge, but I'm still going to learn something in this particular case. So I have Ampere's law, mu naught I enclosed, which we've just said is going to be 0. So I'm going to get 0 as the closed line integral of B dot dl around that loop, which of course then is going to consist of the left integral B dot dl plus the right integral B dot dl plus the top integral, which is the one that we're interested in, B dot dl plus the bottom integral B dot dl. Now here the logic is much like before. For the bottom part and for the left and the right, I expect 0. If we go back to the diagram, you can see the bottom part again is 0 because this bottom part really is at infinite distance from the solenoid. Things really would be 0 far out there. For the left and right parts, again, these are cutting perpendicularly to the field lines, particularly if it's a very, very long solenoid. So therefore, I get no contribution from the left and right sides. I'm just left with a potential contribution along this top side. Is there going to be any magnetic field at that particular location? So these three terms, left, right, and bottom, are gone. What I conclude then is that 0 from the left-hand side is going to equal the integral along that top portion, which will be integral of the magnitude of B at that outside part of the solenoid times the magnitude of dl times the cosine of the angle between them. In this case, notice my loop is looping around in this direction, right? That's how I made it a closed loop that can loop around to form my closed loop. But my fluid model tells me, well, outside the solenoid, the fluid that's been pumped through the center of the solenoid is going to be returning back around the outside. So those are actually at 180 degrees. It turns out it's not going to matter that much since we've got 0 on the other side of the equation, but it's good to get these things properly. And the cosine of 180 degrees gives us -1. The magnetic field is the field strength at that distance outside the solenoid. It's going to be some constant at the constant distance I've chosen. So this is just going to give me the magnetic field outside the solenoid times then the integral of those little pieces of length, dl, which again is just going to give me the width of my rectangle. So I add up all the lengths along this top segment of my rectangle. So that will just give me times L. And this, of course, we can solve. We can simply divide both sides by L, and we conclude that the magnetic field outside a solenoid, if it's infinitely long, is 0, and if it's of a finite length, it's very close to 0, to a good approximation. So that's another neat result for solenoids, that the field is concentrated just inside the solenoid, 0 field outside. Much like it is actually for a capacitor, where the electric field is focused inside the capacitor. So what we really have here is a way of, in an electrical circuit, because I can wire this solenoid up to a battery or a capacitor or to other types of devices, it gives us a way of storing magnetic fields inside our particular device, much the same way capacitors store electrical energy inside of themselves.